Hello, everybody, and welcome to the session where we are going to discuss how to use Elasticsearch to solve a fundamental problem regarding streaming architectures. So, as you may know, the conference is all about solving problems, and in this session, we are going to be discussing the problem of how to minimize the complexity that are inherent when you are dealing with streaming architecture. And guess what? We're going to solve this problem using Elasticsearch. For those of you that don't know me, my name is Ricardo Ferreira, and I'm a developer advocate at Elastic, where I'm part of the developer relations team that focuses on the community and the relationship with anyone that is using the Elastic technologies. Before Elastic, I used to work with other vendors such as Confluent, where I kind of got more in deep with this whole world of streaming technologies. And before that, Oracle and Red Hat. So anything that you want to discuss regarding observability, streaming systems, databases in general, or perhaps if you are a Java or a Golang programmer, feel free to reach out. And by the end of this line, you're going to see my Twitter handle and my blog is here. Feel free to reach out anytime you want it. So without further ado, let's discuss the concept of what triggered the usage of streaming architectures these days. So let's start with this. The reality is that if you think about it, we are experiencing a revolution regarding how we are dealing with architecture. So the world has changed. If you think about it, the world doesn't look like what we used to have 20 years ago, where we would design systems that would primarily think in terms of data as a pile that would be stored somewhere, and then we would write programs that would retrieve that data to compute and take actions upon it. These days, we're talking about a revolution that's a lot of data coming in. The data is very frequent and abundant, so you have to think it differently in terms how do you actually are going to leverage the power of data, because here's the thing, if you don't do it, your competitors are going to do it. There is this very interesting study from Forrester that evaluates the perishability of the data. So the theory is by the time the data actually happens or when the data is actually created, it tends to perish over time. So if you don't take actions as soon as possible, the data happens, you are going to rely on stale data by the time that the timeline passes, right? So if you think about how we design systems today, we use something called the traditional analytics, where, as I mentioned before, you store data and then you compute later. Whereas if you use this approach, you're not going to leverage the power that the context that is inherently in the data that just happened, right? So if you design systems that can react to this data, you are going to create a more sustainable approach where you can identify proactively either opportunities to your business or perhaps identify as soon as possible the threats that can jeopardize your business, right? So as I mentioned before, there is a huge amount of data, so we no longer need to design systems that are basically transactions that will be stored into a database. Now we're talking about telemetry data, we're talking about IT sensors, we're talking about machine learning jobs that are by themselves are generating data that can and should be used as your processing pipeline. So the first architectural paradigm that you have to understand is that this word of starting first and processing later needs to finish. And the word where you are actually going to react to the data as soon as they happen is when you are using this data as they flow through. Forget about this symbol here, what it actually looks like or means, but think about this and into a stream storage that data will flow in, and your queries and your processing needs to evaluate the data as they pass through, right? So the reality is that most people, like very instinctively, think about this data structure over here as a messaging technology, because think about this, it looks like a messaging technology, a streaming technology per se. So it's not very uncommon to see developers adopting technologies such as Apache Kafka or Apache Pulsar and start the designing of their systems. And there is nothing wrong with this approach, right? For whoever is watching the session and you are engaging into an architecture like this, you are doing absolutely right. The problem is only relying on this is not enough, because in the end of the day, you are just creating the pipe, right? But there is a need for an entire infrastructure that can leverage that pipe to actually react to data changes, right? So here's the first thing that you have to take care of it. Messaging and streaming technologies such as Kafka or Pulsar or RabbitMQ, they're great, but they cannot be the only solution that you have to use it for. So we've discussed the need for these the change of this architecture size. So your mindset regarding how you're going to design your architecture needs to change. So that's first. Now let's evaluate how current implementations are actually look like these days, right? Because as I mentioned before, developers are instinctively adopting technologies such as Kafka or Pulsar or any other messaging or streaming broker available in the industry today, but they're getting tricked by the complexity of this technology. So let's discuss this for a second. What I mean by complexity, what I'm primarily focusing on is the amount of plumbing that needs to happen until you actually have a properly end-to-end streaming architecture. So, all right, as I mentioned before, you have Apache Kafka or Pulsar. They are your stream storage. Great. They're scalable, they're durable, they can handle massive writes concurrently. However, they don't provide the means for you to perform processing and querying and analytics on top of the streams, right? In order for you to actually leverage this, you have to rely on other technologies such as stream processing, for example. You can implement using Apache Flink, Apache Spark, you can use KSQL DB, and there's a bunch of technologies available for you to do this, but they are not highly integrated or pre-integrated with your message broker or your stream storage. Although they are compatible, so don't confuse compatibility with pre-built integrations. They are compatible, but there's some fine-tuning that needs to happen before you actually leverage this. And more importantly, those other layers, they actually are distributed systems by themselves that simply augments the complexity of your architecture. So TLDR, you have to take care of and you have to mind the inherent complexity that adopting streaming technologies like this one will bring to your architecture and to your teams. If you look closely, any streaming architecture will look like this. You're going to have this persona of the data source, which is the data that you were aiming to acquire and process and extract some insights from it. And then by the time you actually need this data and think about the actual insights, what we call data analysis, there is 3 common layers that needs to take place for you to start leveraging this. The first one is that what we call the stream storage per se. That would be your Apache Kafka or Apache Pulsar, RabbitMQ, Kinesis, Google PubSub, or whatever technology you were considering to use. And again, those technologies are great. The problem is that they by themselves doesn't do anything, right? If you think about it, Apache Kafka itself like prouds itself to see as a dumb pipe, right? Because in the end of the day, it is a dumb pipe. It's simply a broker that stores messages in a form of the log or streams. It doesn't do anything with the data. For the data to actually end up there, you need a layer called stream ingestion. And we're talking about technologies such as Kafka Connect or producer APIs that you can leverage from Kafka or for Pulsar. So you would have to write your own program for this, deal with the semantics of double acknowledgements or the transactional nature of writes. So there's a whole inherent complexity that you have to worry about in order to bring those streams into Kafka. And after this, you also have to do some kind of a data normalization, data aggregation, data compaction, or data processing in general that usually takes the form of what we call a stream processing. That's where technologies such as Apache Flink or Apache Spark, they take place. So in the end of the day, you are dealing with a very complicated end-to-end pipeline. And like I mentioned before, each one of those layers are distributed systems by themselves. So I brought you here an example of a typical architecture that follows the paradigm that most Kafka adopters tend to use. So in the middle of this architecture, you obviously have the Kafka cluster, which obviously it is a distributed systems complex to be managed. Yes, there's a lot of managed services all there that you can use it or adopt that would offload a bunch of this complexity of managing it. But in the end of the day, you have to mind that they are distributed systems. So how do you bring data to Kafka? You're going to use things like Kafka Connect, which is another clusters, another distributed system. It's by itself it has its own complexity, and Kafka Connect is responsible for read the data from the source and store into Kafka. All right, point number one, we solved that problem. How do you actually going to process this? Maybe your ultimate goal is to bring to Elasticstack or Elasticsearch and do data analysis with Kibana, but in order to do this, you need a connectivity layer that it can be Kafka Connect, it can be Logstash, or it can be any other integration method that you would like to use. But again, those are other distributed systems that you have to manage. And more importantly, the stream processing part, which can be a KSQL DB from Confluent, an Apache Flink cluster, they also need to take place, and they by themselves are distributed systems. And in order for this to handle data, they would need to leverage this entity. This is more like a design pattern than actually a technology, but we call those schema registry. A schema registry is basically an entity that can govern the how the schemas and the mappings for your data will take place, right? So the whole objective of the schema registry is to store schemas such as in a JSON schema format, or maybe on protobuf or Avro, and they would dictate how your layout of your data will look like. Because in the end of the day, Kafka stores just bytes. They don't have format, they don't have a layout, right? So what you have to understand is that schema registry, it will be a permanent layer of your end-to-end architecture. So just to wrap up, we're talking about different technologies, different distributed systems that it is going to be your responsibility to take care of and to actually manage. Apart from this technical complexity regarding the technology that you have to adopt, you also need to observe some new programming modules. So typically, you would be used to things like aggregate data using SQL databases, but programming modules such as temporal analysis, time and temporal analysis, such as analyze the streams in a given period of a window of time, or perhaps doing processing towards causality, which is giving the occurrency of event A, then event B happened, then event C happened, and all of this will actually cause you to absorb knowledge that probably you don't have at this point, and this is going to increase the length of where you are actually going to deliver this product, because this is knowledge that you and your team have to understand first. And finally, the last complexity that we would like to talk about is that Kafka, typical technologies such as Kafka or any other messaging technology, they have a very limited storage. And by storage, I mean, Kafka is a persistent technology by itself. So everything that you write into Kafka is going to be permanently stored into this cluster. And because of this, the cluster actually is associated with storage, and likely this is going to be magnetic disks, which is how people usually design their clusters, or perhaps this could be solid state disks. Regardless, if you want to, for example, have a Kafka cluster whose storage capacity is for 8 terabytes, you can come up with 4 nodes of 2 terabytes each, then you're going to form that cluster. But you don't have the ability to separate things like, all right, my hot data will be stored on these specific nodes over here, and my cold data, which be data that's passed like 6 months ago, would end up into another set of nodes in the cluster. So it has a more uniform story in terms of storage. So that brings you an economic problem to solve, because here's the thing: if you want to grow the storage of your cluster, there is no other ways to do this without necessarily bringing not only the storage or a new node with stores, but also compute, which comprise memory and CPU. So growing storage capacity and technology such as Kafka is not economically viable, right? Specifically, if you're dealing with use cases such as observability or CM or security, that it is interesting to store months or years of data and put them all together so you can analyze it at once. Now you probably have a pretty good idea about the need of streaming architectures, right? Which is they're great, but they impose the challenge of the technology landscape that bring with them these days, and also the problems that are coming with this technology adoption, such as new programming models to learn, as well as the problem of growing the storage capacity. Now let's talk about the solution. So I brought you here some interesting designs that we're going to discuss that is going to leverage features from Elasticsearch that are going to solve fundamentally all the problems that we've discussed here, namely the problem of having multiple distributed systems to be managed, the problem of growing your storage capacity, and the problem of not necessarily learning, or at least taking too much time to learn new programming constructs that you are going to use to process those data streams. So let's start about discussing the most important one, which is a feature for an Elasticsearch called data streams. So for those of you that know Elasticsearch, you know that the unit of storage of Elasticsearch is virtually an index, right? So, and that index can be spread over multiple nodes in your cluster that we call it shards, right? But ultimately, you are going to create like a multiple versions of your index, depending how you're going to partition your data. For example, maybe you are going to partition your data by month, right? So every month you are going to roll out to a new index that's going to store the data from that new upcoming month. But in the end of the day, if you're storing data for 1 year, you are going to end up with 12 indexes that you would need to manage them individually. Data streams solving that complexity problem by creating this virtual entity that we call, guess what? Data streams. And then for the developer perspective, for the API perspective, everything remains the same. You write the data, write documents into the index, you query, you aggregate data from it, but Elasticsearch will manage this escalation of partitioning the data over multiple index, depending on the rules that you specify. For the sake of the other features that we are going to discuss here, data streams are going to be the main building block that we suggest you to be using in your streaming architecture. So TLDR, store all your data into data streams, no longer directly into indexes. The second feature is the concept of data tiers. That this is not necessarily something new in Elasticsearch. It has been available for a while right now, but it is something that allows your team, allows developers to mutate the data and organize the data in a way that you can leverage different hardware configurations in your cluster. So for example, if you want data to be instantly retrieved by the time you put a search that is aimed to query hot data, you can reserve some nodes of your cluster that use solid state disks or perhaps some more advanced block storage, and that data will be allocated automatically. The data streams, the data from the data streams will be allocated automatically in those nodes. Whereas you can maybe you can have some code data where you can use, instead of SSD disk, you can have magnetic disk, which are cheaper. Or maybe if you are aiming to store like rivers of data, years of data, you can put this completely into an object store, maybe on S3 on AWS, or maybe object storage from Google Cloud, or perhaps blob storage from Azure, you name it. So you can use this more economically viable, durable, and cheap storage and still attach to your Elasticsearch cluster in a transparent manner. So again, for the sake of developers, for the sake of APIs, nothing changes. So Elasticsearch cluster will transparently leverage those different types of storages and allocate the data accordingly. And the component that actually does this magic is something called ILM. ILM stands for Index Lifecycle Management, and this is the set of rules that creates a template that you are going to say things like, all right, we're going to dedicate 30% of the data to be hot data. The other 30% of the data will be cold data, and anything else is going to be frozen, go into the frozen tier, and is going to end up in an object storage. So all those rules and the specifics of those rules, such as, for example, if you're leveraging another feature called searchable snapshots, you can minimize and offload the amount of shards that your Elasticsearch might have by enabling the disabling of shards, a certain number of shards if you go, for example, to the code tier, right? So all those rules can be created like in a very intuitive template, and you can simply apply those to your data streams. And a matter of fact, this is a precondition for you to create data streams. Let's talk about how you are going to process that data. First, there are two features that you need to understand. The first one is what we call a transform. A transform is something relatively new in Elasticsearch and allows you to create those continuous processing that you can deploy into Elasticsearch, and it's going to take two parameters, the source and the destination. The source is going to be, guess what, a data stream, right? Or the set of data stream that you want to process. And in a transform, you can use whatever querying and aggregation feature Elasticsearch support. The only condition is that you are going to actually generate what we call an entity-centric index that ultimately is going to be used like in Kibana for analysis purposes. So the beauty of transform is that it scales transparently with your cluster. So if your nodes has the tag that it is a transfer node, the transform will be spread over the cluster transparently for you. So if you want to increase your transforming power, just increase your compute power on your cluster. Secondly, it runs continuously. This is not something that's going to run in batch. Technically, it has a feature where you can set it to batch mode, but most of the time you will want to enable this to run continuously for you. And then you have something called EQL. EQL stands for Event Query Language. This is a language that you are going to use to perform event stream processing and handle those programming constructs natively into Elasticsearch to handle things like time windows analysis and perhaps some causality, such as, all right, given that event E happened, then event C plus event A needs to happen as well. So this type of complex correlation you can express into an EQL language, and they are all applied into a data stream that you previously created. So this is, as you can see here, there's a whole bunch of technology innovations that Elasticsearch introduced in the recent years to deal with this entity called data streams that, as I mentioned before, it's becoming the new style how developers create architectures. To emphasize how you can actually play with all of this, I've brought you this demo here for you where you have this, it is a Pac-Man game, guess what? And the GitHub repository here, and I'm going to provide this link here in the comments in a second, so you can deploy by yourself. But I invite you to play with this demo right now, and the only thing you got to do is grab your tablet or phone and scan this barcode over here, and you're going to be brought to this web application where you can put your name or your alias or whatever you want to be called, and then you can simply start playing with the game. Or if you are watching this using the computer, you can use this URL over here called ElasticCon 2021 storage Google API/index.html. So this is a planned web application that you can simply play with the game Pac-Man, and everything that I've discussed here has been implemented using the building blocks we've discussed, such as data streams, ILM, EQL, transforms, and there is a data tiers configuration that has been deployed on Elastic Cloud that handle this transparently for you. With that said, I would like to thank you for the time you've spent here in this presentation. I hope you enjoyed the Pac-Man demo. And if you have any questions regarding how that demo leverages all the features that we're discussing here, feel free to reach out in the chat or reach out by email. I'll be glad to answer. Enjoy the rest of the conference and have a nice day.